being recorded.
So a few things before we jump into the worksheet again today. The plan, if you look at the schedule, is to continue doing stuff with proofs. Last lecture on Wednesday, we worked through some examples with direct proofs, counterexample, contrapositive, and contradiction, and got, I guess, about almost finished this whole proof worksheet. What I've done, I hope it works. Sorry, the chat's over top of the link for me. Is I've extended this worksheet a little bit. So before we had the last question, question 6, just on the bottom right-hand corner of this page, what I've done is I've still got the addition, the previous exercise we worked through last day. So exercises 1 through 5, but then I've added another proof by induction exercise that we can go through today, and then also a proof, a loop invariant proof. So, I mean, I guess if you want, you can save this as a separate file and have the exercises solutions that we worked through Wednesday in one file, and then the induction and loop invariant stuff today. What I'll do is after lecture, I will upload a solution with all, what is it, 8, 7, or it should be 8 of these exercises. I guess one other thing that I wanted to just touch base on a little bit is if we go to the official course outline, we finished assignment 1. Assignment 2 goes out on Monday, and it's due the Monday after. And also on the horizon is midterm 1, which is, if we're here, it's kind of just over 2 weeks. So between 2 and 3 weeks from now. So it's on the horizon. And the plan is, I was trying to actually finish and publish assignment 2 a bit early, but last night my Microsoft Word froze about 5 times. Then I was up at 6 this morning and spent 3 hours trying to do it again, and my Microsoft Word just keeps freezing when I type in equations. So I'll have to just slowly do it piece by piece and save, and do it a little bit more and save, because it seems to keep crashing when I try and do certain types of equations and symbols and stuff in my Word. I think it's this old laptop just doesn't like it. So I'll certainly have the assignment out on Monday, and it basically covers I guess everything after the discrete math. So we covered discrete math in assignment 1. So it's going to do kind of the pseudocode and counting unit. Obviously, there's some recursion stuff, some proof stuff. And then what we're going to talk about next week is Big O. It's also got some Big O stuff just because it isn't due until the week after. So you'll be able to get the majority of the questions done. And then the last question or 2 just has some stuff on Unit 5. Yeah, so about the quiz, I think I just forgot to click publish. So I guess when I create the quizzes, they're just drafts, and then I usually go through them to preview them just to kind of make sure that the format works, because sometimes the format does not come out as I expect when I do it in the editor. And so I think I did that, and I have to click publish, and I have to click, like, it says, are you sure you want to make this live right now? And I think I must have forgotten to click the yes, I am sure confirm. So I'm not sure what I'll do. I'll see how big the quiz ends up being for Tuesday. If I don't think it's too much, I can just add the quiz exercise onto that one. And if not, maybe I'll just post it as kind of practice material or something. I can look at for some past exams, and obviously I'll try to have the material somewhat similar in terms of the units covered and the difficulty and whatnot, because I am trying to align this with previous semesters. I will say that the format is obviously going to be different. So I guess in all the previous semesters, the midterms have been written on paper. So obviously that's going to be a little bit different. I certainly think certain things are easier to do on paper when we're talking about proofs and doing combinations and stuff like that. So again, it'll cover the same material, and I can try to dig up some and post them, but obviously the format's going to be a little bit different. So I'll have to play around with what I think works, and I typically will kind of come up with all the exercise I want to do, and then I'll again preview it and go through it myself a few times, just kind of see what it's like to actually do these types of exercises in this online setting that the Connects Test and Quizzes tool. So I'll probably do some tweaking from there, and as I make those tweaks, I can make some announcements about the format that I end up with and how that all looks. But yeah, the details right now are that, again, it's going to cover, I think, probably the first 5 units. And the best thing you can do to practice is the exercises we do during lecture. So again, those are just those worksheets, the labs, and the assignments. Again, when I'm building the questions, I'm going to see what I've done. I'll go through all of those types of resources and again try to create obviously similar, not the exact same exercises, but stuff similar in scope. Any other questions before we jump into things? I think what I'll do, so again, typically the midterm is written in lecture. So I think it will be like a 45 or 50-minute exam, maybe 45, just because there might just to account for maybe time kind of logging in and stuff like that. And I think I am going to keep it within the lecture period, just because there are people that have other lectures before or after this, or labs or other things. So again, I can't, I mean, it would be nice to give you additional time, but again, that would be fair to other people that would have to kind of miss another lecture, or even possibly another midterm or something. So I'm going to do my best to make sure that it's doable within the allotted time. And again, as I said, I will probably go through it a few times myself, and then possibly even get some feedback from one of the other members of the teaching team, and then kind of just see what they think, and if the questions are clear to them, and how long it would take them to do it in this online setting. Any other questions? Okay, so what I might do is jump to the worksheet, which is here. And so what I added is, on the worksheet yesterday, I had this kind of formal proof by induction that's given in the textbook and given in the slides. But I also have this, I guess, these more general steps that I follow to complete a proof by induction, where you want to prove the base case by by substituting the base value, which is usually n equals 0 or n equals 1, and show that, again, the statement holds true, the left-hand side equals the right-hand side. Then there's this inductive step where we're going to assume the statement holds up to some value k, and what we want to do is show that if this is true, we're gonna show that it is true for the next case as well, so for k plus 1. And so in showing this, typically we refer back to the inductive hypothesis, so the case that we assume is true, and do some substitution. We've got some practice doing substitution over the past few lectures. So I'm going to scroll back over to the left. And so the first exercise I want to work through, let me full screen this. The first exercise I want to work through is exercise 6, where it says use induction to show that the sum of, I guess, integers from 1 to n is equal to n times n plus 1 over 2. So this is something we've already used this in some of our counting operation exercises. So now we're just going to prove it. So let me get my pen tool out. I'm just going to move the tablet over again. Just kind of place over top of my keyboard. Tablet might not be working. I think that should be okay though. That should be fine. So, okay, I can do this with a lot of text instead. So, again, the first thing we're going to do is start with the base case. In the base case, we have the sum of all numbers from 1 to n, and n is just going to be 1, so the sum of just 1. So on the left side, again, if we've got, try and draw it, I guess. On the left side here, we've got the sum from I equals 1 up to 1, which we know is just 1. So then we also want to prove the right-hand side. So the right-hand side, we've got 1 times 1 plus 1 over 2, which is just 2 over 2. Oops. Which is just 1. So we see the left-hand side is 1 and the right-hand side is 1. So again, the base case typically is quite quick and easy. Any questions about this? So we're going to start here now with our inductive hypothesis. And for our inductive hypothesis, what we're going to do is we're going to assume that this up here is true for some n equal to k. So we're going to assume the equation is true for n is k. So what we're assuming true here is that the sum of numbers from 1 to k is equal to k plus 1 over 2. Now what we want to do, we want to show, sorry. Any questions? It's like, it's okay. So now we want to prove the equation is true for the next case when n is equal to k plus 1. So what we're trying to do is we want to show that the sum of numbers from 1 to k plus 1 is equal to k plus 1, k plus 2 over 2. It's gonna be really tough without my tablet. So what we've got here is, so we're trying to get to this on the right side. This is what we're trying to get to. I'm going to do it by, I'm going to, again, use some substitution to do this based on our inductive hypothesis that we've got up above. So what we've got is, we've got this, we've got this sum of numbers from 1 up to k plus 1. And we can actually write this as saying, let's do the sum of numbers from, oh, sorry, this should be equal. From k, all the numbers from 1, so this is saying sum all the numbers from 1 up to k plus 1. And that's the same as saying sum up all the numbers from 1 to k, and then add that k plus 1 separately. Again, both of these are just summing up all the numbers from 1 up to k plus 1. So this is doing it all in one summation. This is saying sum up all the numbers from 1 to k here, and then add k plus 1 afterward. But as we can see, they're both the same. But the nice thing that we've got here is that this, the sum of 1 to k, is up here in our inductive hypothesis. And that's something that we're saying, we're assuming that the sum of numbers from 1 to k is equal to k times k plus 1 over 2, which I've underlined up there. So I can substitute this into this same equation. So what we're saying here is that if I substitute the blue boxes, I can write this as k times k plus 1 over 2 plus the k plus 1. Does this still make sense? Okay, so I'm just going to rewrite this again one other time. No, how did I do that? So by replacing the two things in the blue boxes. Again, our inductive hypothesis is something we're going to assume is true. We assumed that the sum of numbers from 1 to k is equal to k plus 1 over 2. So I can use these two terms interchangeably. I'm assuming that they're equivalent. So what I've done is I've simply said, okay, summing numbers from 1 to k plus 1 is the same as summing numbers from 1 to k plus k plus 1. Again, this is 1 plus this. The sum of all numbers from is just 1 plus 2 plus 3 plus da 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 all the way to k plus k plus 1. Right? That's just summing all the numbers from 1 all the way to k plus 1. Whereas this is summing the numbers, all the numbers from 1 up to k. So what I'm doing is I'm saying this is summing up the numbers from 1 to k plus 1. This is summing up all numbers from 1 to k. So it's equivalent if I also add a k plus 1 at the end. So what I'm doing is I'm just saying, oh, okay, if I then add a k plus 1 to this, we see that these two are now equivalent. All I've done is I've split it up. So, and then again, from our inductive hypothesis, this thing I've got this blue square here. is, I'm assuming that the sum of numbers from 1 to k is equal to k plus 1 over 2. So I can replace this term with k plus 1 over 2. And then I've still got, maybe I should have put it in parentheses, I've still got the plus k plus 1 left over. Does that make sense? Okay, great. So now I can factor this out. So this is k squared plus k over 2. All I'm going to do is I'm going to say this is actually, I can actually just multiply this by 1. I haven't changed it at all. It's just, all I do is want a common denominator here. So again, if I add all these terms together, this is going to be 2k plus 2. So if I add all I've got k squared plus 2k plus k, 3k, plus 1 over 2. And then we know that this is just k plus, oh, sorry, it should be plus 2. K plus 1 times k plus 2 over 2, which is what we wanted this to be. Oh. So I said what we wanted to do is we wanted to prove that this was k plus 1 times k plus 2 over 2. And we just did that. We did it by using substitution from our inductive hypothesis, which we already assumed was true. So again, typically with an induction, again, what we're doing is we're proving the base case, and then we're assuming that it's true for some k. And I guess the idea here is that we can justify this assumption because we've already demonstrated a valid case when it's equal to 1. So again, we could start this as saying, okay, if I know that 1 works, I just want to, if I'm assuming 1 works, I just want to show that it works with 2. And then if 2 works, I want to show that it works with 3. So again, it's this, I guess, kind of, this is why in previous lectures I kind of talked about this bottom-up approach versus top-down approach. So we're starting with, I guess, the bottom and saying, hey, I know what this is. I can solve this trivially. We see this is trivially true up here. And then we're just saying, so okay, if I know if it's true for a case before, I just want to prove that it's true for the next case. Therefore, I can verify that it'll be true for all cases. So what we said is we're saying, okay, if we know it works for a case before, I just want to show that it'll also work for the next case. And that's what we did here. Any questions about this? Looks okay. I think eventually all I really want to show is that, again, with the k plus 1 case, that we've got the left-hand side equal to the right-hand side. I think, I mean, sometimes different textbooks or instructors might do like a QED or like the little box. I'm fine with that, but I think the more important parts to me are that you're able to do the base case, do the kind of come up with this inductive hypothesis, and then follow through with the inductive step. Any other questions? Okay, maybe I'll scroll down, or I'll scroll down. I'll wait another second for a question, then I can scroll down. What time do we got? Okay. Trivial, just that it's very typically very easy to prove the base case. You're just plugging in values. Yeah. I'm gonna stop sharing for just 1 second. I want to see if I can just go to my display settings and make this make the tablet work. Darn, doesn't want to work. Okay, that's fine. Okay, so we'll go down and we'll do another one. I'll just do it the most. That's fine. I lost my chat now. Okay, so consider the following recurrence relation. Okay, cool. I'll do that. I think it's just because my computer froze like 10 minutes before lectures. I was doing stuff with trying to write out the assignment, and I think somehow when I rebooted the tablets seems to not be aligned. So yeah, I can play with it after. Okay, so yeah, show by induction that the T of n is equal to n plus 1 over 2. Yeah, I'll try that after. I just don't want to do that during case. So again, this is kind of similar to the previous equation, but now I just want to show that we can also do this with the recurrence relation. We can do an inductive proof almost the same way. So the base case here again is going to be that when we're just kind of proving that the case for T of 1, our base case is equal to 1 plus 1 over 2. So we see, first of all, for our base case that when n is 1, it should equal 1. And we also just want to show that, that this also equals 1. So again, we know that from the top, T of 1 equals 1. And we also want to show that 1 plus 1 over 2 equals 1, which is just 2 over 2, which we showed before. So we see that the base case is true. Now, again, we're going to do the inductive step. And we'll again start with the inductive hypothesis. The inductive hypothesis is that we're going to assume for some k of n, so we'll assume true for some n equals k, which is we're assuming that T of k equals so we're assuming that this holds, and now we want to show that the case when n equals k plus 1 is also true. So want to show t of k plus 1 equals so again, we've got, so I'm going to again try to, what I'm going to try to do is get to this, this right-hand side equation. So the left-hand side, what we've got is, we've got t of k plus 1 equals, so now I'm going to look up at our recursive equation here. So our t of k plus 1, oops, our recursive equation up here, I'm going to outline in purple. I'm saying for n greater than or equal to 2, any number bigger than the base case, it's going to be equal to t of n minus 1 plus n. So if I plug that in, I'm going to plug that in here. So what this is going to be is this is going to be t of k plus n. Oh, or sorry, plus k plus 1. So again, I'm plugging this down here. Our n now is actually k plus 1. So it's going to be, again, t of n equals t of n minus 1 plus n. T of k plus 1 equals t of k plus k plus 1. Does that make sense? And now I said in these cases, we often use substitution. So now, again, I know that t of k equals k plus 1. So I know that I can plug in this k plus 1 over 2 and substitute it for the t of k here. And when I do that, I get so all I've done here is I've made this substitution. And now what we're going to see is this is basically the same as this. I think this at this point, this is the same as what we did in the previous exercises, where we've got where essentially what I've got here is I've got k squared plus k over 2 plus 2k plus 1 over 2, which is equal to k squared plus k plus 2k plus 2 over 2. Which is k plus 1 plus k plus 2 over 2, which is what we're trying to get on the right-hand side. So again, we can make this the same type of substitution even when we're working. It works the same way whether we're doing it working with recurrence relations, which is something we've just recently seen for the first time, or I guess probably with maybe the way you'd been introduced to induction in your previous course. How many we got? 10:07. Any questions about this? Okay. I typically do. Not sure the best way to do this one. I'll put the chat on the other side, maybe. Okay, moving the chat to the left side of the screen now. Okay, so I'll actually just use all of this space for this problem. Okay, so or I guess I could, when I scroll up first and I can talk about loop invariant. So I know it was for the video, but again, I think of loop invariant proofs as very similar to proof by induction, where the base case, which I guess more formally for loop invariance is called the initialization, is when you want to prove that the invariant is true before entering the loop for the first time. Again, very similar to the base case where it's typically quite easily done because we're just plugging in our base values. Then the inductive step, which is often called maintenance when it in a loop invariant, but again, kind of directly ties to our inductive step, is that we're going to assume that the invariant holds up to some given iteration, and we want to then show that it holds at the end of this iteration before we begin the next iteration. The new thing that we don't necessarily see in a proof by induction is that for these loops, we also want to show that, again, the loop eventually terminates and that our invariant holds when it does, when loop eventually does end. Because with this verification, we can be certain that our algorithm actually does what it's supposed to do. When the loop finishes, we've got what we want. We show that it's true when we begin the loop at each iteration, and therefore when we complete the final iteration. Any questions about the general, I guess, steps for a loop invariant proof? I'm gonna have to get you to show me after class. Lucas, give me some tips on doing this. Okay, so I'll use all this as my workspace for this problem. So I'll start with the base case on, I guess, just the left here. Oh, sorry, I didn't. Oh, I was scrolled up. I thought Lucas, you said again to do something with edge. But yeah, statement still holds. Before we enter, so what we want to do here is think about before we enter the first iteration of the loop. So before we enter the first iteration, I'll highlight this in red. So before the first iteration, we're right here. So we've got I is equal to 1 and result is equal to 1. And what we want to do, our invariant that we're trying to prove for this is that the result is equal to I factorial. So if I is equal to 1, then I factorial is equal to 1 factorial, which is just 1, which equals the result. So our invariant holds before we actually first enter the loop, because my result's 1, my I is 1, so the result technically equals I factorial. I guess, so now the induction step, which I guess we also call maintenance, I guess that is maybe the more formal way for an loop invariant. And this base case is the initialization. So the induction step is that we're now going to assume at the beginning of iteration k that result equals k factorial. And now we want to show that at the end of iteration k, before, I guess, as we are about to start iteration k plus 1, that result equals k plus 1 factorial. Sorry, I realize now that this is probably a little bit too low for some of you. I know that I should keep it away from the very bottom. I apologize for that. I'll move up for the actual proof part. So again, we've now shown, just to summarize, we've now shown that in the base case, result equals I factorial. We're now going to assume that at the beginning of iteration k, that the result is k factorial. We want to show that after I've finished this kth iteration, that the result is equal to k plus 1 factorial. So now we need to actually take a look at what happens in this loop. And so now we're actually going to look at what happens in this loop. Oh, let me. So in the loop, we've got two statements here. One is incrementing I by 1, and then one is multiplying result by the new value of I. So given that right now I equals k, and I guess from our inductive hypothesis, result equals k factorial. First, we see that I is incremented. So now I equals k plus 1. We then see that I is multiplied with the result, or no, I guess multiplied onto the result. And so from our inductive hypothesis, we know that that before we update our result variable, result was equal to k factorial. So what we've got here is we've got result equals result times this new value of I, which is k plus 1. And we know the result used to be k factorial. So what we used to have is, we're now saying what we're trying to assign as our new value of result is going to be k times k plus 1. And we know that k factorial is actually, and I can just rewrite this as, I'll rewrite this just because it might make it a little bit easier on the next line. I can rewrite this as just k factorial time, or k plus 1 times k factorial, which is equivalent to writing k plus 1. And I'm just going to change k factorial here. So we know that we can write k factorial as k times k minus 1 times k minus 2 times all the way down to 1. Because that's what a factorial is. It's from that, it's that number, multiply that number all the way down to 1. But now if we see that we've got, I replaced the k factorial with k times k minus 1 times k minus 2 all the way down to 1. And now what I've got is I've got k plus 1 times k minus 1 all the way down to 1. So now I'm multiplying all terms from k plus 1 down to 1, which by definition of factorial is just k plus 1 factorial. So what we've done is we've now shown that, or what we want to do was show the result at the end of this iteration is going to be k plus 1, and now we've just done this. The last thing I want to do, unfortunately, I've really botched this in terms of space, is the termination. So the termination, we see that after the loop ends after the n minus 1th iteration. And this is when I finally reaches n. So after our n minus 1th iteration, our inductive step shows that result will equal n minus 1 plus 1 factorial, which is n factorial. So from this, we can conclude that n factorial is returned. So again, at the end of the kth iteration, result was equal to k plus 1 prime, because again, we're setting result to 1 originally. So after our first iteration, I is going to go up to 2, and result is going to be 2 times 1, which is 2. Does this kind of make sense? These 3 parts of our loop invariant? Awesome. 1021. So yeah, a few questions in the lecture in the chat. Yeah, I forgot to actually make the quiz go live today, so I'll either push it to next week, or I'll just kind of release it as an extra bit of an extra practice resource as we're moving towards the assignment and the exam. Yeah, so there'll be another loop invariant on the assignment. We'll try and see some in the labs, and yeah, and I can also try to, again, when I come up with some practice material for the exam, I can try to release some there as well. As I said, we're moving on to, I guess, asymptotic analysis next week, which will be there will be 1 or 2 problems from this unit on the assignment, but we'll make sure that we've covered it kind of next Tuesday and Wednesday, so we'll still have 5 days to complete those last problems. And then I guess in a few weeks, we've got the midterm, and the cutoff will be at the end of this asymptotic analysis unit. So yeah, so I'll be releasing some videos this weekend to show this unit, and then we'll be working through exercises on the next unit throughout all 3 lectures next week, and that will be the cutoff for the exam. That's in terms of answering a question like this on a test, I'm still trying to think of how to actually do a lot of these types of problems in this online format. So I'm going to play around this weekend, and I'll have to provide more details after I've come up with something I think works. Yeah, it could be fill in the blank. That's something that I've been looking at. Yeah, so just what is, yeah, just, I haven't been able to find any options for kind of drawing answers in connects. So yeah, I think it's got to be something like fill in the blank or some sort of multiple choice or something like that. Or if possible, short answer, if it's not, doesn't require a lot of kind of crazy symbols and equations, that you can just be done in normal text. Yeah, exactly, Dave. Yeah, I know, and that's why I'm going to have to determine how to do this, because I understand it takes a lot longer to do some of these things with a keyboard as opposed to just with a pen and paper. Okay, so I'm going to recording here, and as I said, I'll make some announcements this weekend as soon as I have more details about everything. But and I'll also make an announcement when I do release the assignment, which is due on June 1st.
The recording has stopped.
Yeah, thanks everyone. Have a good weekend. And again, I do have office hours now for the next 2 hours.